I'm going to walk you guys through two examples of combustion reactions. Now, combustion reactions are often one of the most difficult reactions to balance. In general, the note in the top right here talks about compounds that have carbon, hydrogen, or carbon, hydrogen, and oxygen can typically burn with air. And when they do burn, the products are typically carbon dioxide and water. So that's just something you need to know with combustion, that it's typically these carbon, hydrogen, oxygen particles that make a compound called a hydrocarbon. And when they do burn, you get CO2 and water, similar to what I demonstrated in class with burning a candle and capturing the vapor, condensing off of it, and doing the carbon dioxide splint flame test. The first reaction I'm going to try to balance for you guys and give you some advice on is methanol burns with oxygen. So I would have to give you in the directions what methanol's formula is. I do not expect you guys to memorize these hydrocarbons like methanol and even propane and the other ones that have been on that practice worksheet previously. So methanol is often written like CH3, which is like methane. However, it's got an oxygen and hydrogen package on it as well. So this whole set of elements is the compound methanol. Now, if we assume it reacts with oxygen, which is diatomic in this case, your reactant should look like this. The products, you need to know that it's a combustion reaction because it's got oxygen, air, reacting with something that has carbon, hydrogen, and oxygen. The only thing it's really going to do is to make carbon dioxide plus water. You do not need to worry about charge balancing this, is because this is straight up molecular compounds. The methanol, molecular, carbon, hydrogen, oxygen. And then we've got oxygen gas. We do not need to charge balance this. Do not charge balance the carbon and the oxygen, the hydrogen and the oxygen over here on water. All we need to do is mass balance it. And mass balancing is the tough part for combustion reactions. So I'll go ahead and try to use the T-chart for you guys. This is probably the tougher example out of the two I'm going to show you. I'm going to start off with carbon. The carbon on the left, on the reactant side, I've only got one. The carbon on the right, I have one. So that seems to be balanced and works. However, once we get into adding up the hydrogen and the oxygen, we might run into an issue. The hydrogen on the reactant side, you got to add them all up. It's not just 3 hydrogen, it's 3 plus this solo hydrogen out here. So there's 4 hydrogen. On the product side, we have 2 hydrogen. Now, it may be tempting to go ahead and try to balance this out and simply make the hydrogens equal to 4 by multiplying the product side by 2 as a coefficient. And we can try that. So if we do that, we take care of the hydrogens, it seems like. However, if we add up the oxygens, on the reactant side, we have 1 oxygen plus 2 oxygen, that's 3. Usually when I have an odd number, that tells me something's going to be goofy, and I might have to do some doubling up from the beginning with carbon. Oxygen on the right, we have 2 plus 1, that's 3 as well. Now it appears that the oxygen is balanced, but I've actually made a mistake. I've got 2 oxygen on the CO2, 1 solo here, but I put a 2 out front just a moment ago. So technically, we have 4 oxygen. and this is where it gets interesting because you could do a common multiple to get out 3 and 4 to be intact with the number 12, where you could put a 4 times 3, but then you have to choose where do you put that 4. How do you adjust the 4 on the left hand side, because you've got oxygen on the compound of methanol, but yet you've got oxygen on the solo oxygen gas. So because you'd have to split that coefficient between two different ones, I already know that's going to give me a problem. So I'm going to restart and I'm going to double the carbon. I'm going to restart with carbon and actually double it up from the beginning. That's a strategy to use once you run into this roadblock. So I'm going to cancel that. Now I'm going to do carbon. And I'm just going to cut to the chase and say I'm going to start with 2 on each side and double it. So now I've got 2 carbon on the reactant side and 2 carbon on the product side. Now I'm going to go back down through and do my hydrogen like I normally would. I'm saving oxygen to last because oxygen's by itself here. And if I have to tweak something, it'll be easy to tweak this solo diatomic oxygen. So technically on the reactant side, I have 4 hydrogen, but times 2. So that's 8. On the product side, I have 2 hydrogen, and that's an easy fix if I put 2 times the 4, and 4 becomes my new coefficient. And again, this is going to mess up oxygen, but that's fine because oxygen is solo on the reactant side. So on the reactant side, I currently have 4 oxygen. On the product side, I have 4 from all the water, 4 times the 1 oxygen, and then I've got 4 from the CO2, so that's 8. Now again, since I have 8 oxygen on the product side and only 4 on the left, this is confusing because the 4 on the left are split between the methanol and the oxygen, but the only one I really want to mess with is the oxygen. So technically I have 2 oxygen already for the methanol, and now to get to 8 I have to add 6 to somewhere. This is where you want to think about how can I get 6 out of the oxygen. If I put the coefficient of 3 out front, that will get me 6 oxygen. So now at this point, I've got all the mass accounted for and balanced out. So again, the combustion reactions are the trickiest. I recommend you start with the carbons, do the hydrogens, and then oxygens. And if you run into something where there's an odd set of particles on the reactants versus product side, then start over with carbon and go up to the next number and see if that helps balance it out. Some of you will be able to do this in your head and you won't need to do the T-chart, and that's fine. Now the next reaction is somewhat easier to set up, and I'm going to use it to balance and to make a prediction. So imagine you have propane that burns with oxygen. So again, I'd have to give you this equation. I don't expect you to know this. Propane is made of carbon, 3 of them, H for hydrogen, and 8 of those. So there's propane, no oxygen in this one for propane, but it does react with oxygen in the air, and oxygen is diatomic. So again, you have to recognize that this is a combustion reaction because there's a carbon and hydrogen compound, and it's reacting and burning with oxygen. The only thing it can really make at this point is carbon dioxide plus water. Now here, we're going to do the T-chart technique again. If you want to try this guessing and checking, so be it. So here's the reactant, here's the product side. On the product side, or excuse me, on the left reactant side, I've got 3 carbon. On the product side, I have 1 carbon. So I'm going to try to balance this out. In order to get the right side to be the products to be 3, I'm going to take it times 3. That would be a new coefficient to try out. Now, of course, the 3 is going to affect the oxygen, but remember, I save oxygen last because oxygen's typically in this reaction sitting by itself, and it's an easy fix. So now I'm going to go on and count my hydrogens. On the reactant side, I have 8 hydrogens. On the product side, I have 2 hydrogens. I'm going to try to balance those now. In order to get the hydrogens on the right to equal 8 on the left, I'm going to take it times 4. Now this method does not easily work if the hydrogens are split between different compounds. That's the problem with oxygen. Oxygen tends to be split between different compounds on the reactant side and the product side. That's my new coefficient. So now on the product side, I have 8 total hydrogen. On the left, I still have 8. Now let's go down and clean it up with oxygen. On the left, I have 2 oxygen. On the right, the total oxygen I have is 2 times 3, which is 6. And then I've got 4 oxygens from the water. So that means I should have 10 oxygens total. Luckily for us, the only thing we can manipulate on the reactant side is the solo standalone oxygen. So in order to get the 2 oxygen to become 10, the coefficient needs to be a 5 as a multiplier. Now if you add these all up, you should have all the masses and all the atoms accounted for the equation. Once that's done, you guys can move on to doing the prediction problem. Now, I'm going to just calculate the element and the compound masses for the items I need for this prediction to speed up and end the video. But again, if the direction said add up all the masses and get all the compound masses and element masses, then do that. So in this case, we want to see how much water can be produced. So I know I need to do the mass of the compounds for water from 80 grams of propane. So I know I need to add up the mass for the propane. Remember, if there's subscripts, you do have to work those in because that's what makes the compound the actual compound. If there's coefficients, leave that 4 coefficient out of water until the end when you use it in a unimultiplier. So for carbon, I have 3 of those. And if you look on the periodic table, carbon should be approximately 12.01 grams. Hydrogens, I've got 8 of those. And if you look on your periodic table, it should be 1.01 approximately. And now we're going to sum all those up after multiplying them. You take 3 times the 12.01, the 8 times the 1.01, and you should have approximately 44.11, if my calculations are correct, for propane. And try to label your final products here when you're doing the multiplication to keep track of what the heck these masses represent, which compound or element. And I'm going to skip oxygen. I'm going to skip carbon dioxide because I don't need it in my equation. So I'm going to go and do the waters compound. I'm going to skip the 4 for now. I'm going to do 2 times the hydrogen. And I've got 1 oxygen at 16 grams. And if you multiply and add those up, you should get 17.01 grams H2O. So that's the mass of 1 compound of H2O. But I'm going to bring down the coefficient also. and do 4 times. The point to leaving the coefficients out again is to see that you guys know how much just one standalone compound has for mass or a standalone element has. And if your mass is messed up or your calculations, I can look to see if you even did the compound mass right using the subscripts. All right, now I have these two compound masses and I can use them to set up ratios to do my prediction. I'm going to fit that prediction in over here below the prompt. Remember the mantra for unimultiplier. Start with what you have, take it times some known ratio to get what you want. In this problem, I have 80 grams of propane. I'm going to write the formula version. C3H8. Now in a unimultiplier, I need to put the thing I no longer want in the denominator to backwards cancel this out. So I know from the recipe or the equation that one package of propane is 44.11 grams. The grams of propane cancel. I know I want to produce and see how much water I can get, so I'm going to use my relationship from the equation where I use the coefficient up front of 4 times the package of water, 17.01 grams H2O. Now if you multiply these across the top for a simplification step, we should get something along the lines of 5,443.2 grams of water. If you bring over the 44.11 and divide those, we should get approximately 123 grams of water being produced. The strategies for balancing these equations and balancing the mass doing unimultipliers is all the same. Just keep the rules straight for balancing formulas. When it's a molecular compound like carbon, hydrogen, oxygen, you do not need to charge balance it. It's only for ionic compounds.